All right, so welcome back, everyone. So today is our pleasure to have George Stepanians, who will be talking about the spectral theory of scalar Volterra equation with application to learning of material laws. Yeah, thank you, George.
Great. Thank you so much, Meridian, for inviting me to speak at MLDS. So yeah, I'm very excited to talk today about a project that I've been working on at Caltech in my first year of postdoc in the group of Andrew Stewart and also with collaborators at MIT. So the main question really is trying to understand how to find closed form solutions for linear scalar Volterra integral equations. And I'll explain why these equations are important, why they're ubiquitous in so many different areas that concern dynamics. And then I'm going to show an application of this theory of deriving closed forms for these types of equations in machine learning for materials science. And these are the two papers concerning what I'm going to talk about today. Okay, so why do we care about Volterra integral equations? Well, they are sort of like the canonical model for filtering of time signals or convolution with one-sided kernels. So you'll see these things come up in statistics and time series analyses and signal processing. They also are the immediate models for evolving the dynamics of partial observables of nonlinear dynamical systems or Schrodinger equations, and I'll show why that is in a second. Also, input-output maps, such as, for example, if you have a dynamical system with a control, your input is the control, your output is the state of the system. So these types of maps, they usually can be expanded through these higher order series called Volterra series. And you can view Volterra integral equations as like the first order approximation to a Volterra series. And a lot of what I'll talk about today is that these types of integral equations are very important for modeling strain-stress relationships in linear viscoelastic materials. And the final thing is, if you take these types of equations and you study them in discrete time, you can also equate the problem of solving Volterra integral equations as the inversion of triangular and Toeplitz matrices. So there's a correspondence between this question in linear algebra and these types of dynamical models. Okay, so my talk outline is going to follow the four sections. First, I'm going to really give a motivation for why Volterra equations are interesting, where they come from. Then I'm going to briefly touch on why we expect solutions for these types of equations to exist. And then I'm going to present a unified theory that we've developed with a collaborator at MIT, showing how you can solve Volterra equations in continuous time, in discrete time, also fractional equations and delay differential equations all under one theory in the linear scalar case. And then we're going to show how this theory applies to modeling materials with machine learning. Okay, so why do we care about Volterra integral equations? So you can view these things as arising from partial observations of linear dynamical systems. So here what I have is a LTI, a linear time invariant system, and it's essentially its state matrix M is positive semi-definite. So I've decomposed it in this block way. And we might be interested only in trying to track the dynamics of the first coordinate Q0. So we don't care about the rest of the coordinates Q1 through Qn. And so we can split this equation into Q0 and the dynamics of everything else. And then what we can do is we can take Q1 through N and we can try to just integrate it out by using the closed form Duhamel's formula for the solution of Q1 to N. And we can plug that back into the equation for Q naught dot. And you can just trust me on this or derive it yourself. It's a relatively easy analysis. What you get back after solving for Q1 to N and plugging it into the Q naught dot equation is a Volterra integral equation where Q naught no longer just depends linearly on its current state, but it actually depends on its entire history through some memory kernel K. And this memory kernel explicitly, it's given by a positive sum of decaying exponentials, a finite sum. And the exponential decays in the sum given by K are exactly the eigenvalues of this lower block matrix A. Okay. I'm also happy to take questions if this part is if people want me to belabor this point, I can give more details. But so this is something that you can just quickly verify that indeed modding out all the unseen variables in your dynamical system, you get back a memory kernel that is a sum of exponentials. Okay, so this is also can be placed in a much more general context for nonlinear dynamical systems, which is called the Morey-Swansig formalism. So you can do the exact same thing for quantum dynamical systems or Schrodinger equations. So here, essentially, I have some finite dimensional quantum system with a self-adjoint matrix H. And again, we can only try to observe the first coordinate of the system, phi naught. And by doing the exact same analysis from the previous slide, you'll find that phi naught also undergoes its own dynamics, where it depends on its memory through some memory kernel K. So it's another type of Volterra integral equation. Except in this case, because our dynamics is complex, K actually is a positive sum, a finite sum of positive Fourier modes. And so this also corresponds to a much more general formalism if you do things for nonlinear dynamics called the Nakajima-Swansig formalism. So there are two kind of classical examples of how these types of integral differential Volterra equations come out of partial observations of dynamics. Okay. These things also come up in the study of viscoelastic materials, which behave linearly when you stretch them. So this is a classical model of a viscoelastic material called the Kelvin-Voigt model. It's essentially this series connection of springs and dampers. And you can look into each one of these boxes and ask what is the relationship between the stress, the force on this box, and the strain or the local deformation. And Kelvin-Voigt just gives this relationship by a damped spring law. So you, of course, have the part that's Hooke's law saying that force is some spring constant EI times the deformation epsilon I. So that's the elastic term. But you also have this damping, which is saying that you also need to add the friction coefficient or damping coefficient nu I times the time derivative of the deformation. Okay, so this is the Kelvin-Voigt model. And you can take it to the continuum limit where these boxes get smaller and smaller and you have infinitely many of them. And in that limit, you can imagine that now your material can be sampled at any point x from 0 to 1. And locally, it obeys this type of a constitutive law, which gives you the map from the strain at that point, epsilon of x comma t, the local deformation, and the stress at that point, sigma of x comma t, which are the local forces that are felt. Okay, so this is the Kelvin-Voigt model. And a natural question that people are interested in with this model is, can we relate the spatially average strain, so the total deformation of the material, to the spatially average stress, or the total forces that are felt in this material? So one thing to note is because of Newton's laws, in this one-dimensional chain, all the forces sigma I, they need to just cancel, they need to be equal to each other. So that means that no matter where you sample this material, the force sigma of x comma t at that point should just equal some constant, which I call sigma bar of t. Okay, so that's one useful observation. So now we can take this equation and we're interested in averaging out the space dimension x. So first we're going to take a Laplace transform of this equation. So now that I've taken Laplace transform, sigma becomes sigma hat and epsilon becomes epsilon hat. And the only thing that's changed is that the time derivative in epsilon now becomes a multiplication by s in the Laplace domain. So I've taken a Laplace transform in time, and now this is my new equation. Okay, so here on the left now I've introduced what I mean by average stress and average strain. They're essentially just the average over epsilon of x comma t and sigma of x comma t over this unit interval in space 0, 1, where the material lives. So now what we can do is we can actually derive a relationship between average strain and average stress. So to do this, we're first going to divide through by this multiplicative factor E of x plus S nu of x, and then we're going to take spatial averages. And what we see from this is that in the Laplace domain, so if we transform t into S, the relationship between average stress and average strain is given by this type of equation. So if there's questions up to this point, I'm happy to detail this. But essentially, all we've done is we've taken Laplace transforms, we've divided through, and then we've taken spatial averages. Okay, so eventually we want to transform back out of the Laplace domain, back into the time domain. So let's do that now. So here what I've done is I've just slightly rewritten this equation where I've pulled out 1 over nu of x from the integrand. And I've done this suggestively because if we transform back into the time domain, we know that anything of the form 1 over a plus s corresponds to a decaying exponential e to the minus at in the time domain. So generally, we actually find by transforming back into the time domain that the average stress, or like the total forces felt in this material, if you convolve it with some exponentially decaying kernel K, it gives you the total deformation or the average strain in this material. And you can see exactly that K of T here looks very similar to this expression in parentheses at the top of the slide, where now each one of the exponential decays is given by E of X over nu of X. Okay, so this is yet another example of how these types of Volterra integral equation memory-dependent models come up now in material science. Okay, so to talk about this a little further, a natural question in material science is, like, we know that we have this model, and it's naturally described as going from stress to strain. So we know if we're given a time series of how the forces in this material evolve, we can convolve it with this kernel, and we can predict the total deformation epsilon bar of this material. So a natural question now is, can we invert this relationship? So if we've done a bunch of experiments and we've learned K, can we learn the inverse of this map from epsilon bar to sigma bar? And material science answers this question affirmatively in a special case. Essentially, it says that if K is a finite sum of exponentials, sometimes this is called a Prony series, then through some simple Laplace transform, just high school algebra, you can show that there is a inverse relationship from epsilon bar to sigma bar, which is given by another type of Volterra integral equation. So it's saying that sigma bar depends instantaneously on epsilon bar and epsilon bar dot, but now also, again, on a memory term on the entire history of epsilon bar convolved with some new kernel J. And this kernel J is also going to be a finite sum of exponentials. So material science was able to answer this question in this like relatively limited case. And so part of the reason of this project that I'm discussing was coming out of frustration of not being able to find a general solution to this problem. If K is an actual infinite sum of exponentials, there really was no progress on this result, which meant that you couldn't really study the Kelvin-Voigt model in the full generality. Okay, so we talked about where these types of equations arise in dynamics, in material science. Now I want to give you maybe a little bit of intuition of why we expect solutions for these equations to even exist, why we expect that they should be invertible. Okay, so we saw in the previous slides that Volterra equations that we looked at, they had kernels which were given by sums of exponentials, or possibly integrals over exponential decays. And these types of kernels are called completely monotone kernels because they're decreasing, and no matter how many times you differentiate them, essentially they still look like monotonic functions, but their derivatives are changing sign. So that's what it means by completely monotone. And so there's been a lot of investigation in the material science community dating back to the 50s and likely earlier on what the solutions of Volterra integral equations are when their memory kernels are infinite sums of exponentials or completely monotone. And like I mentioned before, material science has had a really tough time making progress on this question outside of the simple case where K is a finite sum of exponentials. So there's been some work, but I'll explain why it was in some sense not complete. However, in the theory of Volterra integral equations, there are very clear existence theorems stating that even if you have a kernel that's an infinite sum of exponentials, you should be able to solve these things in closed form and find inverses to these equations. So clearly there was this gap between what we could do in practice and what the theory of the equations was telling us. And recently there's been some progress trying to close this gap, but it still has not addressed the full generality of the problem. Okay. So why do we expect Volterra equations to be invertible? Well, a natural kind of a natural thing you can try to do is take a continuous time convolutional equation like this. So it's a special type of Volterra equation, and you can discretize it in time. So I've really just turned this integral into a Riemann sum. I'm assuming that my delta t is 1. So essentially you have this type of a discrete time equation resulting. And then, of course, you can see that this now corresponds to this type of a linear system. So if we want to solve this equation, if we want to recover x from y, then what we have to do is essentially invert this triangular Toeplitz matrix that's given by the entries of K. And we know how to do this. This is really just given by forward substitution. So this is an O of n squared algorithm. You essentially just peel off your solution one at a time. You first divide y of 0 by k of 0. That gives you x of 0. Then you plug it into the next line and so on and so on. And so this is an O of n squared algorithm, but nevertheless, it gives you a procedure for always being able to solve these types of convolutional equations in discrete time. And the same sort of idea holds in continuous time. We sort of expect that this type of intuition should carry through even in the continuous time setting. Also, one thing to mention, this is also an explanation for why one-sided convolutional problems like this are much nicer than two-sided convolutions. So in general, Volterra equations are nicer to solve than Fredholm equations. Okay, so now let's focus a bit more on this discrete time convolution problem and look into what people in signal processing would try to do to solve this problem. So here we have essentially the same equation that we had on the previous slide. And the way that we would solve this problem in signals processing is we would try to transform everything in the spectral domain to turn convolution in the time domain into a product in the spectral domain. And so a natural choice of transform to apply to move us into a spectral domain for discrete time signals is the Z transform. It essentially just takes a time series and it transforms it into a power series. So if we do this, you can verify that actually now we have an equation where indeed we take the Z transforms of all of our quantities and the convolution becomes a product in the spectral domain. So this is sort of the main kind of focus of a lot of this deconvolution literature in signals processing is you transform into a spectral domain, then you divide through by your filter in that domain. So you compute 1 over h of z, and now this gives you your deconvolution filter g of z. But of course, this is something that is in the literature known to be ill-posed because you don't want to be dividing by places where h of z drops to 0. So in practice, there's all sorts of regularizations that people come up with. So you can add a small epsilon into the denominator. You can remove the regions where h of z drops to 0. Or you can do some Tikhonov regularization, which people also call Wiener filtering. So there's a whole zoo of different approaches for deconvolution. And one of the things that I really want to show with this talk today is that you don't have to do this type of regularization to solve the original problem. And we'll discuss why. And the reason for it is because there's really only isolated places where h of z drops to 0, and you can take care of them exactly. So you don't have to do any sort of regularization. So this will kind of be a departure from traditional ideas in signal processing. Okay, so really just to summarize, solutions of Volterra integral equations or essentially like developing theory when we know that they're solved is really has been an open problem for quite a while. There's a lot of literature on existence and uniqueness and regularity theory that doesn't give you any sort of closed form analytic formulas. Material science has really only been able to touch this question in the case of finite sums of exponentials or other special cases. And there's a whole bunch of techniques of trying to solve these equations, which we want to sort of unite under a general theory. Okay, also there's various other interesting examples of Volterra integral equations concerning fractional and delay differential equations, which our theory will also subsume. Okay, so now I want to discuss really what our theory is going to do to unite all of these disparate classes of Volterra equations. So there's largely 5 classes that we focus on. Essentially, there are discrete equations, which are shown in orange. They're the ones that we just discussed in our signal processing section. There's continuous time equations given where the kernels are given by sums of exponentials. We call these things completely monotone equations. They're shown in the green box. There's Volterra equations in continuous time whose kernels are given by sums of Fourier modes. We call these things positive definite kernels. And then also in the red and purple boxes, we have fractional differential equations and delay differential equations. So with these 5 classes, we actually show that there is a way to solve them analytically by reducing them all down to solutions of discrete Volterra equations. And so we'll discuss how this works in a second, but I want to first focus on actually how do we solve discrete Volterra equations to begin with. Okay. If there's questions up to this point, please ask.
Yeah, I have a small question. You finally mentioned the delay differential equations. Do you hear me?
Yes.
Okay. So what would be the connection between the delay differential equation, the delay element, and the tau in the convolution term.
Yes. So if you take a memory kernel which places delta functions at different lags tau, this gives you a delay differential equation. So that's the connection. That's how you can view delay differential equations as a special case of general Volterra equations. You just have to choose a special type of memory kernel.
Okay, thank you.
Yep. Great. So now I want to talk specifically about how we show that discrete-time Volterra equations can be solved in closed form. And then I'll explain how all other types of Volterra equations in these 5 classes can be reduced to solving discrete-time equations. Okay, so if we take an equation like this, here essentially it's saying that you have some time series x, you convolve it with some kernel k, possibly also adding on a constant multiple of x at the current time, and that gives you your observed signal y then. So the first thing that we do is we use exactly the same procedure from signals processing, and we transform this equation into the spectral domain. So we do this using the one-sided z-transform, which again takes a time series and turns it into a power series. So if z is chosen to be e to the in theta, then you can think of this exactly as just taking a Fourier transform, a discrete Fourier transform of a signal. So if we do this, then we again see that in the spectral domain, our convolution has turned into a product. So capital Y is a z-transform of little y, and capital X is the z-transform of little x. Okay, so we want to really study the z-transform of our kernel K further. And what we're going to assume is that K is a positive definite kernel, meaning that it comes from a Fourier transform of a positive measure on the circle. Okay, so there's some distribution on the circle. It gives us all of the Fourier modes of K. And if we actually study then what is the z-transform of K given by this type of a positive measure, we can just do some quick analysis. We can expand this power series that the z-transform gives us. And eventually we find that the z-transform of K is given by the spectral measure lambda integrated against this integrand that depends on z. Okay. So we have some nice structure on what the z-transform of K is when K is a positive definite kernel. So then what we can do is we can split z of K into 2 parts. We can split it into this integrand ratio, which is a very well-studied complex analytic object, which I'll discuss in a second, called the Cauchy transform. And we can also get some remainder, which is just the mass of the spectral distribution of K, which is lambda. Okay. So then roughly speaking, what you get at the end is that we've been able to transform z of K into some constant plus the Cauchy transform of lambda. So really all this is saying is that if you make this assumption that K is a Fourier transform of a positive measure, then you have some very nice structure on the spectral transform of K, and it's given by this quantity Q of lambda, which I'm going to discuss in a second. Okay, so then the main thing you want to do in signals processing is you want to invert this thing in the parentheses and move it to the other side, isolate x of z as a function of y of z. So we need to study what the reciprocal of this quantity is in more detail. Okay, so what does the Cauchy transform actually do? This is a classical complex analytic object. What it does is it takes a distribution on the circle, lambda. So lambda is giving us all of the Fourier modes of our kernel K. And it complex analytically extends it into the disk. So what I mean by that is that it creates a holomorphic or analytic function in the disk such that the boundary data of its real part, if you just read off what its real part is doing on the boundary of the circle, it's exactly giving you the distribution lambda that you started with. So it's a very kind of important object because it gives us the solution to analytic extensions on the disk. Okay, but what we're interested in studying, we have some constants that might appear also that are added on to the Cauchy transform. So we need to study what this like shifted Cauchy transform is. And all it is really is you take your original Cauchy transform and you just add sigma to the imaginary part. So we call this thing Q sub sigma. And this is really the quantity that we're interested in taking the reciprocal of. And so what you can show is that if you have a shifted Cauchy transform Q of lambda plus some shift I times C naught, then taking its reciprocal, if you just plot it and stare at it, it really looks like a Cauchy transform of something else. So you haven't really left this class of shifted Cauchy transforms by taking reciprocals. And in fact, you can actually verify this mathematically, that indeed, when you take reciprocals of these kinds of objects, you get back another shifted Cauchy transform given by some other measure mu and offset zeta naught. And so you can prove this rigorously through something known as the Herglotz representation theorem. Essentially, all you need to verify is that you have this object Q of lambda plus IC naught. It's an analytic function. It doesn't drop to zero anywhere in the disk. So I can safely take its reciprocals. And then I know that the real part of its reciprocal will still be positive. And then the Herglotz representation theorem tells you that any analytic function on the disk with positive real part is given by a Cauchy transform of mu, of some measure mu. Okay. So once you have this type of result, it's very easy to understand how to get from lambda to mu, because you just take this reciprocal, you read off the real part of the reciprocal, and that gives you back the distribution mu. Okay, so just to summarize, essentially, we can also split Q of lambda into real and imaginary parts and write out a more explicit formula from lambda to mu. It's not too important. To summarize, really, the main procedure for taking reciprocals of these Cauchy transforms is you start with some spectral distribution lambda, which gives you all of the Fourier modes of your kernel K. You form this shifted Cauchy transform. You take 1 over it, and then you know now that this corresponds to another shifted Cauchy transform of something else. And then this gives you back another spectral distribution mu and offset zeta naught. So in summary, this gives you a map from lambda and C naught to mu and zeta naught, and we call this thing the interconversion map. Okay, so you actually deriving this map always holds is quite complicated, because you can have settings where the measure lambda drops to 0 on the circle, in which case this division by lambda squared might actually not make sense. You might have a division by 0 occurring, and you have to do a lot of work to show that in the places where lambda drops to 0, you actually have atoms appearing in mu. So that's something that if people are interested, I can talk about more, but for the purpose of this talk, it's not crucial. Okay, so this is really kind of what was missing in these prior theoretical works in the material science community, is they weren't able to kind of grasp the full complexity of this mapping from the map of the spectral distribution lambda to a map of the spectral distribution mu. So their formulas were missing certain terms that were quite important. Okay, but to summarize really what we did, we started with a discrete Volterra equation that looks like this, where K is the Fourier transform of a positive measure lambda on the circle. We took Z transforms to put this into the spectral domain. Then we took reciprocals, and now we know that the reciprocal is also given by a shifted Cauchy transform. And finally, this tells us now that if we take inverse Z transforms, this corresponds to a new Volterra equation, which now maps Y to X, where the memory kernel J is given by a Fourier transform of mu. So essentially, our interconversion map B, it's allowing us to find a map between the spectral measure of K and the spectral measure of J. That's really its whole purpose. Okay, so that's enough for the theory. Let's actually verify that this works. So we can start with a discrete time Volterra equation that looks like this, where again, K is a Fourier transform of a measure lambda on the circle. And we can apply our interconversion map that we just discussed to get an inverse equation from Y to X, where the memory kernel J is given by a Fourier transform of the spectral measure mu. And then we can test this on an example. So we can take K coming from the Fourier transform of this blue measure lambda. Our interconversion map tells us that the spectral measure of the inverse kernel J is given by this red density mu. And so we can plot the Fourier transforms of these measures, and this is giving us back our original kernel K and the inverse kernel J. So this is what they look like. And then what we can do is we can play the following game. We can create a time series in X, and we can plug it into our convolutional equation on the left to get back a time series for Y. And then we can take that time series for y and plug it into the equation on the right to reconstruct x. And we see that this reconstruction agrees with the original time series for x very accurately. So indeed, our theory is correct, and it's giving us back the exact inverse for this problem. Okay. So just to briefly mention, we can, like I mentioned at the start, we can map the other classes of Volterra equations to the discrete Volterra equations. So there's a way to solve them, continuous time equations, fractional equations, delay differential equations, using the theory that we just discussed for discrete time equations. So I want to just very quickly mention this for these two classes of equations that I've highlighted, completely monotone equations, which look like this. Essentially, they are Volterra equations whose kernels are given by positive sums or possibly integrals of exponential decays. And like we mentioned, these come up in the study of viscoelastic materials. They come up in various interesting dynamical models and partially observed dynamical systems. And the second class we want to study are positive definite Volterra equations in continuous time, where K is now a sum of a positive sum of Fourier modes. And so these come up, like we mentioned at the start, in partially observed quantum systems, and really for any sort of time-dependent dynamics where you're trying to convolve your dynamics against a RKHS kernel, like a Gaussian or an exponential or something else. Okay. So the main difference from the previous section that we studied in discrete time is that these distributions lambda, they no longer live on the circle, they actually live on the real line from -infinity to infinity. So our previous theory does not immediately apply because it was interested in working with measures on the circle, and that's not our setting here. But you can still apply it in the following way. You can take lambda, which is this blue distribution on the bottom left, and you can lift it up by a certain mapping called the Mobius transformation onto the circle. And then we can apply our interconversion map on the circle and then map back down onto the real line. And so we can complete this commutative diagram, and essentially now we have a map from lambda to mu on the circle, which we call the real interconversion map. Okay, it has a lot of interesting properties. And now I just want to play the same game and verify to you that indeed this interconversion map allows us to invert Volterra equations in continuous time. So here on the left, I have a continuous time Volterra equation where K is given by a sum of positive exponentials. So it has it's a Laplace transform of some real spectral measure lambda. So here I've plotted lambda. It's just a uniform distribution on 0, 1. And our theory, our interconversion map BR tells us that the Laplace transform of J, essentially the weights of all of the exponentials in J, are given by this inverse spectral measure mu. Then what we can do is we can actually plot K and J to visualize them. And now we can verify that indeed these two equations are inverses. So we can take a random trajectory in X, we can plug it into the equation on the left and get out a trajectory for Y. And then we can plug it into the equation on the right and see if we reconstructed X. And indeed, we get a very reasonable reconstruction this way. Okay. And you can do the exact same thing when your kernels are Fourier transforms of real measures and show that the theory exactly inverts them there. So that's really just the main kind of point that I want to make, that all of these equations, whether they're in continuous time, discrete time, and also if they are fractional or have delays in them, they can all be studied under the same types of analytical formulas, which is something that really wasn't properly investigated before. Okay, so now the last thing that I want to discuss, really, this is a machine learning seminar. I want to discuss how some of this theory motivates the use of certain machine learning architectures in the simulations of materials. Okay, so if we go back to this Kelvin-Voigt model that we started with, if you remember, we said that it was a material built up of this chain of springs and dampers, and then we could take it to a continuum where essentially at every point x in the unit interval, the deformations or strains, which we called epsilon of x comma t, were related to the stresses or the local forces felt in this material as sigma of x comma t by this type of a damped spring law. Okay, and then what we did is we said, okay, we're actually interested in how the total deformation epsilon bar of this material is related to the total forces felt in this material, sigma bar of t. And we were able to derive this expression that actually there was a Volterra equation that was relating the forces felt sigma bar to the deformation epsilon bar, and it was given by a convolution of sigma bar against a memory kernel k, which was an infinite sum of decaying exponentials. Okay. So just for notation's sake, now what I'm going to do is write this kernel more generally, k of t, as a integration of e to the minus alpha t against some spectral measure lambda. K of t is an infinite sum of exponentials, so you should be able to represent it in this way. Okay. But now that we actually know how to solve Volterra equations in closed form, we know that there exists a map from epsilon bar to sigma bar. So we know how to invert these types of equations. And indeed, our theory now tells us that the relationship from epsilon bar to sigma bar is given by another type of Volterra equation with memory kernel j of t also given by an infinite sum of exponentials. So we start with an equation where k of t has spectral measure lambda, and we end with an equation where j of t has spectral measure mu. Okay, so our theory is now really telling us that there's a way to invert this equation, and we still get that the map from epsilon bar to sigma bar is a convolution against the kernel with an infinite sum of exponentials. Okay. So now we're going to actually try to simplify this expression because we don't always want to keep track of like all of the infinite number of exponentials in J. This is not numerically, it is not something you want to store in memory. So instead what we're going to do is we're going to approximate J by a finite sum of exponentials. So in particular, you can imagine that Jn of t is coming from a Laplace transform of some spectral measure mu n. Okay, so then you can actually rigorously show from this that J and Jn, these two kernels, are not too far apart from each other. In fact, as you add more and more decaying exponentials into Jn, the difference between them should decrease at a rate of 1/n. So we have, based on this theory that we've developed for Volterra equations, we now actually know that there is some exact rate at which you can approximate the memory kernel J, and it converges pretty quickly as you add more exponentials into Jn. Okay, so what this is telling us now is that it's perfectly okay to model the map from strain, the total deformation in your material, to stress, sigma bar, where you're convolving epsilon bar against a finite sum of exponentials. And now kind of the final trick after we've had this insight is that this type of a model above can be entirely rewritten as a linear ODE that's forced by epsilon bar and gives us sigma bar. So you can verify that essentially each one of these exponentials, beta I e to the minus alpha it, is now replaced by the dynamics of some coordinate psi I. So if you integrate out psi I, you exactly get back a convolution of epsilon bar against an exponential decay. So all of this analysis is now telling us that if you take this type of a linear viscoelastic Kelvin-Voigt material, the map from its average strain to its average stress can be modeled quite accurately by a linear differential equation that's forced by strain and gives you stress. Okay, I'm happy to take questions or discuss any piece of this if there are questions. Okay, so that's essentially the gist of this, is that our theory now tells us that if you take a linear viscoelastic material, then indeed it's very well approximated by a linear ODE of this form. And so the main insight now is that we want to generalize this class of models because not all material models are going to have linear relationships between strain and stress. So we take this linear ODE and we generalize it now where the right-hand sides possibly can be nonlinear functions, such as neural networks. So everything has stayed the same, except now we've just generalized the types of functions that can appear in the right-hand side of our model. But importantly, this model still has the fundamental property that it's trying to encode memory effects in the mapping of the strain, the deformations, to the stresses, the forces. Because when you take any sort of a material, such as a viscoelastic material or possibly plastic materials, when you deform them, the deformations are actually memorized in the configuration of the material, and then the kinds of forces that it stores up based on how you deform it depend on the history of deformations. And so these types of ODE models are able to capture these types of memory effects. Okay, so really you take this type of neural ODE model and together with some sort of a numerical integration scheme, you're now able, for any input deformation, you're able to predict the evolution of stress in this type of a material. And so this gets applied quite successfully both in the setting of linear materials, such as the viscoelastic ones that we've talked about in this presentation, but also it gets applied widely for nonlinear materials, exactly because we've been able to replace our linear ODE with a more general nonlinear dynamics. So we show in a follow-up paper that actually this type of idea can also be applied in the simulation of multi-scale materials, where essentially on a very small scale, the material is having variations in its microstructure. And we show that these types of neural ODE models can be very effectively embedded into global finite element simulations to simulate the deformations of these types of materials. And our goal in the future is extend this past 1 dimension to 2 and 3 dimensions, now that our theory is telling us that these types of neural ODE models can approximate the dynamics of various materials. We're interested to extend this to higher dimensional problems. And so that's where I want to end for today. Thank you very much for listening, and I'm happy to take any questions.
Yeah, thank you very much. Any questions or comments?
Yes. When you started, you were talking about average strain and average stress.
Mm-hmm.
The question would be, what type of averaging can make a difference in the conclusions?
Yeah, I mean, so the main thing people are interested in is you have like a small piece of material, and you're not able to just dissect this material into smaller pieces. You just have what you have, and so you're interested to understand, if I apply this type of a global deformation, then what are the total forces felt in this material? So that's why averaging is performed.
Yeah, but I can try different types of averaging, and also there is some information that is being lost by talking about the average.
Yes, but from the purposes of an observer that's interacting with this material, that's all you have to go off of.
Okay.
You can't continue peeking into smaller and smaller pieces of this material and seeing how locally things deform. You just stretch it, and that's the only measurement you have of this material, is how globally it changed in length, which is what epsilon bar is trying to model.
Okay, now the tau in the convolution
Mm-hmm.
is actually a time shift, right?
It's accessing earlier parts of the trajectory of
So it's a
sigma
time.
bar.
And how is that related to the shift in the Cauchy transform?
So in the Cauchy transform, there is no shift. It's just taking a measure on the circle and filling it into the disk.
So
Yeah,
it's transform measures?
Yeah, so if I go back, the Cauchy transform
I think
is
you had shifted Cauchy transform.
Oh, I see what you mean. The shifted, so that's a different type of shift. These are separate concepts. The shifted Cauchy transform is just applying an imaginary shift to the original Cauchy transform. So these are not related objects.
Okay, lastly, the measure mu and the measure lambda. You probably explained it, but I missed it. How they are related?
Absolutely, yeah. So lambda is giving you is a spectral measure of K. It's giving you all of the spectral information you need to reconstruct the memory kernel of your forward equation. Mu is a spectral measure of J. It's giving you all of the information you need to reconstruct the memory kernel of your inverse equation.
Okay, so last, there is something called RKHS
Mm-hmm.
that is very powerful in signal processing and in neural
Yes.
networks, etc. There are courses about it.
Yes.
And I don't think it was mentioned here, but maybe
I
don't
did, yes.
consider it.
Yeah, so we're able to study convolutions against RKHS kernels because an RKHS kernel is positive definite, which means that it's a positive sum of Fourier modes. So like a Gaussian is a classical example. Fourier transform of a Gaussian is going to be another Gaussian. So all of these things can be studied with our theory because we're able to apply our theory to a general class of convolutional equations where K is a positive definite kernel. So any RKHS kernel falls in this class.
Okay, thank you for this beautiful survey. I learned a lot about signal processing, which I didn't know.
Thank you. Yeah. Are there other questions?
Yeah, thanks. Yeah, okay, seems not. Yeah.
Mm-hmm.
Any last questions, comments? All right, yeah, seems not. Yeah, thank you, George, for the nice talk, and then thanks everyone for coming, and yeah, see you all next week, and George, sometime soon. Yeah.
Thank you.
Bye.